Then we still have Team 6, the lecture summary sheet, and I still have 2 copies of the my lecture notes, section 9A to section 9B, so have this out. Okay, and so here is the plan. Okay, so right now we are at periodic functions, Fourier series, formulas for Fourier series, coefficients, even in odd periodic functions, even periodic functions and expansions, so on and so forth. And this is the future plan. I'm excited about this plan. Close the door. Okay, but my goal is to coach you to do report 4 problems before we come back and do more theoretical aspect and more fun. Okay, so I'd like to begin to open today's lecture with always as usual. This is my handwritten note and with annotation that you have seen before. Okay, so we discussed a lot about linear independence, dot product and things like that, and projection. So you have seen the gram matrix. Okay, now the gram matrix also play an important role when we get into Fourier series. Okay, because as I mentioned before, Fourier series or Fourier basis functions are the equivalent of the Cartesian coordinate basis vectors. They are orthogonal to each other, so therefore the gram matrix would be diagonal. Okay, and keep that in mind. This is very important. And with that, I'd like to make a comment on problem 4.2, which I did already mentioned last time. Okay, so this is to make a connection. This is a big picture here also. To make a connection between standard eigenvalue problem and mechanics of materials, particularly the search for the principal stresses and the principal direction. As I mentioned, you have the solution guide, so I'm not going to the detail, but what I'd like to point out is the very nice geometric interpretation of the method to look for the eigenvectors. Okay, and I provided here. Let me put on the mask. Okay, so we are focusing on problem 4.2, and here I provide you with a remark written. So I'm explaining the geometrical meaning of the coefficients of the eigenvectors. Okay, in the method to find the eigenvectors as I explained in class, right? Meaning setting certain coefficient equal to 1 and look for the other coefficient. So 2 things that I'd like to show you. My handwritten notes are from fall 2014, last semester, meeting 44, and also there's a video that you can watch to have additional explanation. But here I just want to show to you quickly. Okay, and so here is my handwritten notes with annotation that I added after class, meeting 44 last semester. So think of this as the eigendirection, right? And when you set the first coefficient, maybe I would have written somewhere. Let me zoom out to check. Maybe not. Yeah. Okay, so let me remind you the notation to refresh your mind. When you solve the standard eigenvalue problem. So recall standard eigenvalue problem. Say, for example, with the stiffness matrix, or can be with any matrices. Okay, you can also deal with the stress matrix, but let's think of it in terms of the stiffness matrix. So K phi equal to gamma phi, let's say, right? And phi, in the case of a 2 by 2 system, 2-degree freedom system, would be a matrix. Let's say phi 1, that you have phi 1 1 as the first coefficient and phi 1 2 as the second coefficient. Okay, so that's the notation to review for you, and therefore in my notes here, that's the kind of notation that I meant. So when you set the first coefficient equal to 1, right, you can think of, okay, you have two coefficients, and a vector would have two components, right? The two coefficients in the matrix are the two components of the vector. So the first coefficient is like the first component of the vector, and the second coefficient would be the second component in the vertical direction, right? So if you set the first component to 1, then the second component is essentially the slope of this straight line here. And so that's the geometric interpretation of when you set the first coefficient to 1. And when you do the problem 4.2, if you follow this method, then the slope that you would find would give you this very beautiful formula that you saw in mechanics of materials. Okay, and that's this one. Let's see. Let me see the principal direction. Yeah, this formula here. Okay, that corresponds to the slope, the second coefficient in the eigenvector, or in the case of mechanics of material, that's called the principal stress direction. Okay, you would obtain this formula. These are the two eigenvalues when you solve the standard eigenvalue problem. Okay, so that's all I want to make as a remark. If you have questions, feel free to ask. Otherwise, I'd like to continue my program for today. And my program for today is, let me close this. I wanted to do something, but let me focus on helping you with report 4. Okay, a student asked me before class regarding the deadline and the extension that I mentioned. So if you go into this is the home page of our course here, okay, EGM 4313, and you go to assignment, and if you look at yeah, I should have gone back to let's see, how do I, back to list. Yeah, so if you click at report 4, right, and student view, yeah, you would see that right now the report will be accepted for resubmission until March the 30th. That's Monday, but I will extend to Tuesday, as I mentioned. So you have more time. But remember that I have cut down significantly already the number of problems, so please don't delay. Okay. So what I want to do next, the plan is to, I believe, to continue to talk about 4.6 that I already started last time. At least that is that would be a motivation, and then we'll look at what would be the ingredients that you need, or at least the street fighting techniques that you need to do this. Okay, so recall that I already pointed out a few keywords, right? From last time, so you see even, odd, of course you see Fourier series, you see period, and then I asked you to do everything but report only this problem. Okay, so street fighting Fourier series, and that's, go back to the daily lecture summary and scrolling down. So this Fourier series story consists of, in fact, the 4 sections. 9A, 9B, 9C, and there's also 9D. Okay, 9D is a section related to successive integration by parts, which I already showed you before. So now let me begin with a little on 9A, in section 9A, and move directly to 9B and then go to 9C. Okay, 9C would be related to even or odd half period extension. Okay, so that's the plan. So 9A, I just want to show you the definition of odd function and even function in section 9A, and so also called section 9. This is the notes that I wrote in since spring 2012. Okay, and I expand the notes and add more sections after that, so that's why it has the name 9B and 9C. Okay, so let me put 2 windows on section 9A so that you see where I'm navigating to. Okay, so periodic functions, I already mentioned. We'll come back to this later. Okay, more theoretical aspect. I'd like to point out the following important formulas. Okay, so here I have already explained in the last lecture how to remember the relationship between the circular frequency, the period, and the period. Okay, let me use a middle window to zoom in. All right. So we are back to the end of the last lecture. Okay, so you see this expression here is the expression for Fourier series. Okay, and keep in mind that A0 is a coefficient, but think of it as multiplied by 1. And with 1, together with cosine and sine, form the basis, the Fourier basis. Okay, and here you note that n is the summation index that goes from 1 to infinity, and in the argument for cosine we have n omega x. Right, x is the independent variable that could represent time or space depending on the type of problem that you are solving. Okay, and similarly, the coefficient for cosine is named a sub n, and keep in mind when n equals to 0, cosine of 0 is 1, so therefore it's logical to use a to denote the coefficient, the constant. Okay, because cosine of 0 is 1. Sine of 0 is 0, and 0 cannot be counted as part of the basis. Okay, and the coefficient for the sine function is denoted by b. Okay, so b sub n, and n is the summation index. Okay, so what you want to keep in mind is that you see omega, the circular frequency, and the way to remember the relationship between omega and the period. P is the period. Okay, this is the period. And P is equal to 2L. The reason that Kreyszig introduced the variable gap L is simply to split the period into two parts, and there's certain advantage. Okay, when you want to look at a function, whether it's an even function or odd function, so we'll come to that. So, but keep in mind that P is equal to 2L, and we want to find the relationship between the circular frequency and the period. Okay, and so this is the method here, right? So I'm not going to go back because it's my lecture is videographed, and you can always look at the video. Now, what is important is that omega is equal to 2 pi over P, and P is equal to 2L, so therefore you can also express omega as pi over gap L. Okay. So now the next point is how to find the coefficients A0. Let me clear out the ink here. Right? How to find the coefficient A0, AN, and BN given the function f. Okay, and that's that should be given above also. I think let me not moving here. Let me keep, sorry, and go to my small windows so that you can see the big picture. Be clear, and let me move over here. Okay. Yeah. So these formulas are also called the Euler formula. Okay. Let me explain. It's very simple. If you just want to apply the formulas, it's very simple. To understand the concept, why why things are written that way, it takes a little more work. Okay, so maybe it's good that I introduce some notation without getting into the details. Okay, and that goes as follows. Maybe just one case. Yeah, just this case. Okay, so let me zoom in. There are two cases here. So this is the case where you pick out a period. Okay, so you see from here to here is one period. And as you see here, P is equal to 2L, right? One period means that the same graph here, the same plot, is repeated periodically, right? So this is one period. And initially, you have the origin of the coordinate system sitting anywhere arbitrarily. But you want to move it to the middle of the period and define a new variable x bar. The original variable is x, okay? But just keep in mind that x bar goes from minus L to plus L, okay? Where L is half the period. Now in the x coordinate, let me write down here. This is the x coordinate, and whereas this is the x bar, and the origin of x bar is right in the middle of the interval from A to B. Okay, so you can relate gap L to A and B, right? Because 2L, which is the period, is simply B minus A. Okay, and therefore that's equal to 2L. So you can relate L to A and B. L is B minus A over 2. Okay. Now let's go on this window here and just look quickly at the formula, okay, related to x bar. So here what you want to notice is the following. Let me zoom in. So the Fourier series is now written with with x bar, okay? Expand it with x bar. So let me go to the middle window, and so that I can, first I zoom out so that you see where I'm moving. I'm moving up to find those formula. Oh, I need to move down, I think. Okay, yeah, right here. Okay, so these are called the Euler formulas, and I'm zooming in. Let's look at, but I need to show to you one more thing. Oh, yeah, it's at the bottom. So let me zoom out right here. Okay, so I just reverse the order. The Fourier series is now written in terms of x bar. Okay, and so this is the function f in terms of x bar. So the question is to find the coefficient a bar 0, a bar n, and b bar n. Now, these are the formulas here. Let's look at a bar n and b bar n, right? And then we look at a bar 0 later. So a bar n, you see it's 1 over L, and L is half the period. Integral from minus L to cap L of f of x bar cosine of n omega x bar. Right? That's the formula, very simple. If you just apply the formula. And the formula for the coefficient b bar n is similar, and the difference is simply integrating using sine instead of cosine. That's all. And let me note down here. One way to remember is, for example, b is the coefficient for the sine term, right? And so therefore you expect to see sine inside the expression for b bar n, okay, as part of the integrand. And likewise, if you look at the coefficient a bar n, okay, a bar n is a coefficient for cosine of n omega x bar, then you expect to see cosine of n omega x bar in the integrand. Okay, so that's how you remember. And now let's look at a bar 0. If you remember, I told you, and I don't even, let's see. Let me scroll up. Okay, this is a bar 0. Right, you only have f of x, and you think of this is f of x times 1, right? And remember, 1 is cosine of 0. Right? The integral is from minus L to L as usual, but the factor now is 1 over 2L instead of 1 over L. So what I was trying to say is the following. If you think that you just, to derive the expression for a bar 0 from a bar n, if you think that you just replace n equal to 0, then you would get a bar n, right? But unfortunately, that's not true. There's a factor 1/2 that you need to keep in mind. Why? We need to get into the derivation of these coefficients. But let's think about the interpretation. Okay, let's think about the interpretation of a bar 0. Right, let me ask the class. So this is good opportunity for active learning here. What can you interpret a bar 0 for? That's team 6. Team 6. Pick up your lecture summary sheet. If you integrate a function over the interval from minus L to L, that's one period, right? And you divide by the length of that interval. What would be the physical significance of this formula? If you integrate a function, maybe a picture is worth 1,000 words. If you have, let's say, like that, and if I have a function, maybe something like this. Right, and let's say the interval would go from A to B, for example. And let's say this is a function f of x. Right? What would be the physical meaning of the integral of f of x dx from A to B, and then divide by 1 over B minus I? How do you interpret this? Is there a physical meaning to this? So we have Paul, we have Dylan, right? Dylan, anyone else? We have Frank. Okay, so let's start with Frank.
Isn't it the average value?
Average, very good. Dylan?
Let's say the average.
Paul?
Yeah, I was going to say it should
Okay.
be the average.
Yes, that's the average.
Divided by the base.
Yes, you're right. The average of the function. Okay, so let me find my list here. So listing 37. So Paul is what team number? Team 3. And Frank is team 7, I think. Yes. And Dylan is
Team 3.
team 3. Okay, very good. So that's it. This is the interpretation for the coefficient A0, okay, in the Fourier series, right? The first coefficient in the Fourier series, and let me zoom out so you can see the Fourier series underneath. And so this coefficient here, and this is the formula. So the first term in the Fourier series represents the average of the signal. Okay, and in electrical engineering, this constant function is called the DC component, the direct current component. You know, electrical engineers use a lot of Fourier series because they deal a lot with periodic signals, you know, electricity and things like that. Okay, so the first term, the average, is called the DC component. And so that's it. So in a way, if you just want to apply formulas to find Fourier series, this is all you need to know. Right? This is the basic. This is the starting point. Now, to do a little more details, in order to address this problem 4.6, okay? Now you are given essentially a parabola and an interval here. Okay, so between minus 2 and 2, 1 minus x squared over 4, right? And you're asked to see whether this is an even function or odd function. So the next concept would be the concept of even function or odd function. Let me poll the class first. How many of you know the definition of an even function or odd function? So if you know, then I can do a little quicker. So 2 is 3 people. Okay, 3 students. Okay, so maybe let's do this. Let me go back to the small windows here, and then I'll ask for contributions. Okay. And let me go down to this. I believe right here. Okay. Yes. So this is the formal mathematical definition of even function and odd function. Okay, so essentially, an even function is when you have f of minus x equals to f of x, and an example is the parabola. Okay, a picture is worth 1,000 words, so let me bring you now quickly to section 9C. Okay, and this is section 9C, and you can see keywords like even or odd, half period or half range extension. And here I look at I take an example of a parabola defined only on the interval from 0 to 1. Okay. So this is the function that you are given, and usually in practice, when you work in industry or in any practical work, you would be given only a function over a finite interval, right? Here is a representation. The nice thing with Fourier series is that you can extend this function into an even half period extension or odd period extension. This is an even function. This is a parabola that goes from -1 to +1, right? And this is a picture of an even function. What does it mean? It means the following. First, the mathematical definition, or let's say the geometric interpretation of the mathematical definition. What it means is the following. Okay, if you take any point x, right? If this is x, and therefore this is minus x, right? For an even function, the value of f x is equal to the value of f minus x. Okay? If the two values are equal, then you say that this is an even function. And geometrically, an even function is a function that is symmetric with respect to the vertical axis, right, the y-axis. Okay, so that's the definition of an even function. And for the odd function, this is the mathematical definition. It's basically anti-symmetric.
I know what it is.
Excuse me, please. So the first part is for the even function, that's symmetry, and for the odd function, that's anti-symmetry. Okay, and it's characterized mathematically as follows: the value of f at minus x is equal to minus the value of f at x, and an example would be like x, the straight line. But here, let me give you this. In section 9C, again starting from just one branch of the parabola going from 0 to 1, right? You can extend this function into an odd half period extension that goes as follows. Before we get into the Fourier series, okay? And so that here. Okay, so if you, within one period, So one period from -1 to +1. This is the original function here, right? The extension is to make an anti-symmetric part, okay, with respect to the origin. What does it mean? So let's look at the geometric interpretation of the formula again. If you let me clear out the ink here, so that it's not so messy. So if you take a point x here, right? So minus x is over here. Now the value here is f at minus x, right? And the value at x is f at x, right? So if f at minus x is minus f of x, then you say that this function over the period from -1 to 1 is an odd function. You see, it's anti-symmetric relative to the origin. What it means is that, to find the mirror image of this point, you draw a line through the origin and you get to the other side. So this is the geometric interpretation of an odd function. Okay. Let me go back to this problem. Okay, so the next step is to find the Fourier series. Okay, so odd and even now you know how to determine not just geometrically but also analytically. Right? So Fourier series. What is the Fourier series of an even function or an odd function? Okay. So with this, let me go back to the formula that is centered about the period. So you see the integral is from minus L to L. I'm really sorry. Okay. So let me ask you this. Over one period that is centered with the origin at the center of the period, let's say if f is an even function, right? So here is an if, okay? If f is even, as in the problem number 12, 1 minus x squared over 4, something like that, right? A parabola. Actually, it should look like this, right? So f is even. Let me ask you this. Is cosine even or odd? Raise your hand. Active learning credit. So we have 1, 2, 3. We have Robert, Kyle, Kevin, and I'm sorry, I need to learn your name. William. Yeah. I remember William. I just need to learn a few times. Okay. So William. Let's start with William. So is cosine function an even function or odd function? Even, and we have Kyle agree and Robert agree. So now we have Kevin agree, and now we have 2 more hands. So Derek and Matt agree that cosine is an even function. Very good. So let me note down. So we have Robert, That's team 5. Kyle is team 6, right? We have Kevin, team 6. And we have Matt. Matt is team 8. And Derek is also team 8. Okay, so, easy questions, so just jump in. But now this is more difficult, more challenging. And the contribution would be worthwhile. Okay. Now, everyone would know that sine function would be what? An odd function, right? What would be the result of this integral without computing the integral? So we have one hand, two hands. Anyone more? So William, Robert. Yeah. Oh, Kenny. Yes, of course, Kenny. Very good. So let's start with Robert, Kenny, and then William. Right, Robert, go ahead.
Would be 0.
0. Okay. And so why?
You have a positive section and a negative section that are exactly the same.
Okay. But you have the function f here. Okay, so let me ask William and Kenny to add on to what Robert was saying. I mean, the answer was correct. The answer is that the integral would be 0, but the explanation, you need to build more explanation to this. You see, I mean, yeah, it's true that the sine function is an odd function, but the integrand is not just the sine function; it's the sine function multiplied by f. Okay, so it's not obvious that the integral is 0, unless you say something more. Well, let's William and Kenny talk first, and then you want to add something to what Robert said and to what I just said?
Because the origin is at the center, and then I was going to say on the left side, the left side would cancel out the right side, because one whole side would be negative, one whole side would be positive, and when you add.
Yeah, in a way that's what Robert was saying. But sine function is an odd function. But in the integrand you have f times sine. So you need to say something more. You want to add something?
I was going to say the same thing. I just know that because it's an even function, and you can basically call it
What is an even function?
That's the Fourier series that we're looking at. Even function.
Yeah.
Making over all parts of our
Okay, that sounds more like recipe, right? No, it's correct, but it's still, we want to find an explanation here. So, Kyle, you want to add something?
The sine function is going to make it approach 0 when at 0.
Yeah.
Due to that multiplier, and then that's the intercept afterward at x equals 0.
Yeah, I mean, look at the integrand. The integrand is f times sine. Okay, it's a product of two functions. So we have Casey and Mark and William. So let's Mark and then Casey. Okay, Mark.
The sine part itself is 0, so fx times 0 is 0.
Sine of what is 0?
So the sine part is 0 is 0, sine is 0, and you find out the function is 0.
You want to integrate the sine first? Remember, this is the integration of the product f times sine. So you cannot just integrate sine alone. So if William, you want to add something more before Casey
I
talks?
just had another idea, which I'm not sure. Which
Very good. What's the new idea?
Because f of x is even, as we said right there, it's not going to change like the sign of the total function. The sign of the function is going to be based off of sine, which is odd. And so when you multiply by the even function, it just is going to like take it to
Yeah.
Okay. Casey?
Didn't because any even function times an odd function creates another odd function?
an even function times an odd function is an odd function, and it's very similar to what William just said. And so what is the formal rigorous proof? You know, it's a good intuition. So here is how it goes. You are looking at let's say the product of two functions, right? F and G. Okay, and let's I shouldn't use F because that could be confused with the original function F. So let me call H. Okay, and just to be in order, let me move H to the second position. So you look at the product of G times H, and let's say G. No, yeah, okay. So G is an even function, and H is an odd function, right? And so let's say the result is call it R result, right? And you want to test whether this is odd or even, so you want to look at R of minus x. R of minus x is G at minus x times H at minus x, right? And since G is even, G at minus x is equal to G at x. Okay? And since H is odd, so H at minus x is equal to minus H at x. So therefore the result is minus G at x times H at x, and that's equal to minus R at x. So therefore, formally, you have proved that the product of an even function and an odd function is an odd function. Okay? And because f times sine, I'll come to you, Frank. So let's go back to this slide here. F is even and sine function is odd, so therefore f times sine is an odd function. So therefore, all of the coefficient b bar n would be equal to 0. Frank?
Well, I was just thinking if x squared is an even function and x cubed is an odd function, multiply those together, it would be
X to the power 5 and x to the power 5 is an odd function.
Alright, that makes sense.
It's an odd function. You can use the decimals or any graphing calculator to verify also. Okay, so the result is the following. For an even function, all of the coefficient bn, b bar n would be 0, and therefore you have something called the cosine series, okay, like Kenny mentioned. So this would be the result of the problem 12 in R 4.6, that you would have cosine series. And how to compute the coefficient a bar 0 and a bar n is just by applying the formula to integrate. Okay. So lecture summary.
I would like to see you take it there.
I started, I was just like, using Word to put all your powers, so you could do it.
You can do everything in Google Docs except for just only you can.
I just wanted to, but yeah, actually, I was doing this last time.
Yeah, I didn't see that. That was fine. Yeah, that's not too bad.
That was looking into it.
Yeah, it's just well.